Right now, tonight, two telescopes are pointed at the same universe, asking the same question. They are giving two different answers. One measurement says space is stretching at 67 kilometers per second equant for every 3.26 million light years of distance. The other says 73, not a typo, not a rounding difference, 2 decimal places apart. A real, measured, rechecked gap between two numbers that are supposed to describe the exact same thing. You are standing on a piece of space that is stretching by two different amounts, depending on which clock reads it. Sit with that for a second, because it does not resolve the way you want it to. This is not a case of one team being sloppy and one team being careful. Both numbers have been checked, rechecked, verified by different instruments, different scientists, different decades of work, and they still refuse to agree. Here is some of what is waiting for you in this story. A void of space nearly 2 billion light years across, so empty it may be hiding the Milky Way itself inside a hole in the cosmos. Dark energy, the force that pushes the universe apart, showing signs in the newest data that it is not constant at all. It looks like it is weakening, dying, in some sense, if the trend holds. And a physicist working out of New Zealand who has proposed something that sounds almost too strange to say out loud, that dark energy does not exist. That the entire idea was a mistake born from not accounting for how time itself flows differently across a lumpy universe. Here is the part that should stop you. This gap between 67 and 73 is not a rounding error. It is a 9% disagreement on the single most important number in cosmology. The one number that tells you how old the universe is, how big it is, and how it ends. And here is the part that makes it worse. For over a decade, telescopes have gotten sharper. Methods have gotten more careful, and every single improvement was supposed to make this gap shrink. It never has. It has gotten worse. Two of the most trusted numbers in physics produced by two of the most careful teams working today. And neither one will back down. Something is wrong. Not with the measurements, with our understanding of the thing being measured. If you want to sit with a real scientific crisis instead of a manufactured one, hit subscribe. Prepare yourselves. We begin. Picture a long, empty hallway. At one end stands a scientist holding a ruler. At the other end, a different scientist holding a different ruler. Both are measuring the same wall. Both have trained their whole careers for this exact task. And when they call out their numbers, they don't match. One says the wall is 67 feet long, the other says 73. Neither of them is bad at their job. Neither of them made a careless mistake. They measured carefully, checked their tools, checked them again, and the wall still refuses to have one length. That is the situation cosmology is in right now, except the wall is the entire universe, and the ruler is something called the Hubble constant. Here's what that number actually is. It describes how fast space itself is stretching, not galaxies flying outward like debris from an explosion. Space, growing, expanding, carrying everything inside it farther apart. The Hubble constant puts a number on that stretching, measured in kilometers per second equant for every megaparsec of distance. A megaparsec is about 3.26 million light years. So the number tells you, for every chunk of that size between you and a distant galaxy, how many kilometers per second faster that galaxy is receding from you compared to 1 megaparsec closer. It sounds technical. It isn't really. It's just a speed dial for the universe. But here's why this single number carries so much weight. Get it right, and you can work backward to calculate the age of the universe, because you know how long expansion has been running to reach today's size. Get it right, and you know how big the observable universe actually is, because you know how far light could have traveled while space kept stretching underneath it. Get it right, and you have a real shot at knowing how everything ends. Whether space keeps expanding forever into a cold, empty dark, whether it slows and reverses into a crushing collapse, whether something stranger is waiting. This one number touches all three. So you would think, with a number this important, that scientists would have settled on one solid answer decades ago. They have not. There are two ways to measure it, and they come from two completely different directions. One side reads the ancient light left over from the birth of the universe, light that has been traveling for almost 14 billion years, and calculates from that early snapshot what the expansion rate should be today. The other side does not look backward at all. It watches galaxies near us, right now, measuring how fast they are actually receding in the present moment. Two methods, two different eras of cosmic history, two teams of scientists, each convinced their number is correct, because they have every reason to be. And here are the actual numbers. The early universe side lands on 67.4. The local, present-day side lands on 73, sometimes higher. This gap has been checked. It has been rechecked. Different telescopes, different countries, different scientists who have never worked together, arriving at the same split. Every attempt to close it has failed. It just sits there, refusing to move, daring somebody to explain it. To understand how we got two rulers measuring the same war, you have to go back to the night there was only one ruler, and nobody had picked it up yet. The place is Mount Wilson, up in the mountains above Los Angeles, where the air is thin and dry and the sky holds still. A man named Edwin Hubble works there most nights, alone at the eyepiece of the largest telescope on Earth, a machine with a mirror 100 inches across. Hubble had trained as a lawyer. He boxed a little, served in the war, then walked away from all of it toward the stars. By 1929, he was not famous yet. He was just a man with steady hands and a lot of patience, spending his nights photographing faint smudges of light that nobody could quite explain. Here is what every serious scientist believed at the time, including the smartest man alive. The universe was fixed, static. It had always looked the way it looked now, and it always would. Stars might drift a little, nothing more. When Einstein first solved his own equations of general relativity, the math kept telling him the universe should be expanding or contracting, never sitting still. He didn't believe it. So he added something to force the math into agreement with what everyone assumed had to be true. A fudge factor. He called it the cosmological constant, and he built it into his equations for one reason: to keep the universe standing perfectly still. Hubble didn't set out to break that idea. He set out to figure out what those faint smudges of light actually were. Astronomers called them nebulae, and most assumed they were clouds of gas sitting inside our own galaxy. Hubble pointed his telescope at them night after night and found something nobody expected. Individual stars buried inside those smudges, the kind of stars whose true brightness could be calculated precisely. And when he worked out how far away those stars had to be for their light to look so faint, the answer broke the Milky Way wide open. These weren't clouds inside our galaxy. They were entire galaxies of their own, sitting so far away that our own galaxy was just one neighborhood in a much larger city. Then Hubble did something even stranger. He measured the color of the light coming from these galaxies, watching how it stretched toward red the way a train horn drops in pitch as it pulls away from you. Almost every single galaxy showed that same stretch. Almost everyone was moving away from us. And the farther away a galaxy sat, the faster it was fleeing. Picture a balloon with dots painted across its surface, someone slowly blowing air into it. Every dot moves away from every other dot as the balloon inflates. No dot sits at the center. No dot is special. Each one, if it could look around, would see every other dot retreating from it in every direction. That is exactly what Hubble had found written into the light of 100 distant galaxies. Not an explosion with a center. Space itself, stretching, carrying galaxies apart the way that rubber surface carries the dots. Einstein heard about it and did something almost nobody does. Traveled to California to look at the data himself. He sat with Hubble's numbers, checked the plates, and walked away convinced. He went back to his own equations and tore out the fudge factor he had inserted years earlier, later calling it the greatest blunder of his career. That night at Mount Wilson, Hubble wrote down a number, a rough estimate of exactly how fast this expansion was running. He had no idea that number would still be unfinished business 100 years later, that entire careers would be built and broken trying to pin it down, that it would eventually split into two numbers that refuse to become one. Here is where most people get the picture wrong, and it is worth fixing before we go any further, because everything after this depends on it. Galaxies are not flying apart the way debris flies apart after an explosion. Nothing is being thrown. Nothing is rocketing through empty space on its own power. If you picture the Big Bang as a bomb going off, with galaxies as shrapnel racing outward into some pre-existing void, you have the wrong image, and it will trip you up later. Here is the actual mechanism. Space itself is growing. The galaxies are barely moving relative to the space immediately around them. What is happening is that more space keeps appearing between them. Think of a loaf of raisin bread going into the oven. The raisins are not swimming through the dough. Each one sits exactly where it was placed. But as the dough bakes and rises, it expands everywhere at once, and every raisin ends up farther from every other raisin. A pair of raisins that started an inch apart drifts a little. A pair that started 3 inches apart drifts a lot more, simply because there is more dough between them doing the expanding. Nobody moved. The space between them did all the work. That is what is happening between galaxies right now, tonight. Space is rising, and it explains something that would otherwise make no sense at all. There is no center to this. If you were floating inside that loaf of bread as it baked on any raisin in any part of it, you would look around and see every other raisin pulling away from you. Not because you are special, not because you sit at some central point. Every single raisin would report the same thing. Every galaxy anywhere in the universe sees every other galaxy fleeing from it. There is no cosmic center that everything is running away from. There cannot be, because expansion is happening equally everywhere all at once. Now, push this idea out far enough, and it turns genuinely strange. Nothing is allowed to move through space faster than light. That rule holds everywhere, always. But space itself is not a thing moving through space. It is the stage, not an actor on it. And the rule was never written for it. So at a great enough distance, the amount of new space appearing every second between us and a distant galaxy can add up to more than light can cross in that same second. That galaxy is not moving away from us faster than light. The distance between us is simply growing faster than light can close it. Some galaxies out there right now are past that line already. Their light, leaving tonight, will never reach us. Not eventually. Not after a long wait. Never. The space between us is opening faster than that light can swim across it. They are gone from our future, permanently, even though they still exist. So here is the problem that follows directly from all of this, and it is the one every scientist in this story has had to solve. If galaxies are not objects you can travel to, touch, or bounce a signal off of and wait for an echo, how do you measure the distance to one at all? How do you put a number on something you can never reach? That question is where the real work begins. You cannot stretch a tape measure to another galaxy. You cannot send a probe and wait for it to radio back a number. So, astronomers built something else instead, something that works almost like a staircase, where each step only has to reach high enough to grab the next one. They call it the cosmic distance ladder, and it works exactly like a ladder should. Each rung is a different method of measuring distance. Each rung only works for a certain range, and each one has to be calibrated using a rung directly below it. You do not leap straight to the top. You climb, one step at a time, trusting that the step underneath you is solid. The bottom rung is the simplest, and you have already done a version of it yourself without realizing. Hold your finger up in front of your face. Close one eye, then switch to the other. Your finger appears to jump against the background behind it. That jump is called parallax, and the closer your finger is to your face, the bigger the jump looks. Astronomers use the exact same trick, except instead of switching eyes, they use the width of Earth's orbit around the Sun. They photograph a nearby star, wait 6 months for Earth to swing to the opposite side of its orbit, then photograph that same star again. Against the distant background of much farther stars, the nearby one appears to have shifted position slightly. Measure that shift, do a bit of geometry, and you have a distance. No guessing, no assumptions about brightness. Parallax is beautiful because it is direct. It is also limited. Once a star sits too far away, the shift becomes too small to detect, even with the sharpest instruments we have. The bottom rung only reaches so far into the dark before it runs out of road. Here is the part that should worry you a little. Whatever error, however small, creeps into that bottom rung gets carried upward. Every rung above it is calibrated against the one below, which means a tiny mistake at the base does not stay tiny. It compounds, it stretches. By the time you have climbed all the way to the top of the ladder, out to galaxies billions of light years away, a fraction of a percent error at the bottom can have grown into something that actually matters. So the entire ladder depends on getting every single rung right, and 2 rungs above parallax matter more than all the others combined. The first is a class of star that does something almost musical. It pulses, brightening and dimming on a steady, repeating rhythm, and the speed of that rhythm turns out to be directly tied to how bright the star truly is. Measure the pulse, and you know the true brightness. Know the true brightness, and compare it to how dim the star looks from Earth. You can calculate exactly how far away it sits. The second is a type of star that does not pulse at all. It explodes. And when it does, it explodes with almost exactly the same true brightness every single time, no matter where in the universe it happens. That kind of consistency is priceless to an astronomer, because it means the explosion works as a marker visible across almost the entire observable universe, far beyond where the pulsing stars can reach. These two, the pulsing stars and the exploding stars, are the rungs that carry the ladder out to serious cosmic distances. And they are also, not coincidentally, the exact rungs the SH0ES team leans on to arrive at their number of 73. Which means, if there is a hidden flaw somewhere in this ladder, if some small crack in the reasoning is quietly inflating that number, it is hiding in one of these two rungs. Finding that crack, if it exists at all, has become something close to an obsession for an entire generation of astronomers. At Harvard, in the early years of the 1900 seconds, there was a room full of women bent over glass photographic plates, working for pay that came in below what a cleaning lady earned. None of them were allowed near a telescope. That was work for men. The women were given the leftover plates, the negatives already captured by someone else, and told to measure and catalogue what was on them. One of those women was named Henrietta Leavitt. She was methodical in a way that borders on relentless. Day after day, plate after plate, she measured the brightness of stars, comparing images taken on different nights, hunting for anything that changed. Most stars sat still, burning at a constant brightness for as long as anyone had photographs of them. But a certain kind of star did something different. It pulsed. It brightened, dimmed, brightened again, on a rhythm you could set a clock to. Astronomers had a name for these already: Cepheid variables. What nobody had was the reason they mattered. Leavitt found it by doing something nobody else had bothered to do. She lined up dozens of these pulsing stars, all sitting inside the same distant cluster, which meant she could be reasonably sure they were all roughly the same distance from Earth. And once distance stopped being a variable, a pattern jumped out at her that changed astronomy permanently. The Cepheids that pulsed slowly were consistently brighter than the ones that pulsed quickly. Not roughly. Precisely the clean, predictable relationship. The slower the pulse, the brighter the true light. Here's why that single fact is worth an entire chapter. If you know exactly how bright a star truly is, and you can measure how dim it looks from where you are standing, you can calculate the distance between you with real precision. It works the same way a candle does. A candle held an arm's length away looks bright. Push it across a football field, and it looks like a faint speck, even though nothing about the candle itself has changed. The dimming tells you the distance, as long as you already know how bright that candle burns up close. Leavitt had just handed astronomy an entire population of candles scattered across the galaxy, each one telling you its true brightness simply by the speed of its pulse. Hubble picked up that rule and used it to end an argument that had been running for years. Was the Andromeda smudge a cloud inside our own galaxy, or something else entirely? He found Cepheids buried inside it, timed their pulses, calculated their true brightness using Leavitt's relationship, then compared that to how faint they looked through his telescope. The math placed Andromeda far outside the boundaries of the Milky Way, not a nearby cloud. A separate galaxy sitting at a staggering distance, one among many. Leavitt's pulsing stars had just proven the universe was bigger than anyone had dared to claim. That rule never stopped working. It is still doing the heavy lifting today. Cepheid variables sit at the center of the SH0ES measurement, the backbone underneath the number 73. Every galaxy SH0ES uses to calibrate its distant supernovae first gets measured through its Cepheids. Using the same brightness to pulse relationship, Leavitt worked out over a century ago. But that dependence is exactly where critics have started circling. Cepheids sit inside the dust and crowded starlight of their host galaxies, and dust can make a star look dimmer than it truly is, which would throw off the whole calculation. Crowding is worse. If a Cepheid's light blurs together with a neighboring star, too faint to separate out, the measured brightness comes back wrong in a way that's difficult to catch. Nobody has caught it yet, but it remains the loudest objection waiting in the wings, the thread every skeptic keeps pulling on, hoping the entire number at the top of the ladder comes apart. Not every star burns out slowly. Some go out in an act of theft. Picture a white dwarf, the collapsed core of a star that already lived and died, packed so tight that a spoonful of it would weigh tons. It orbits closely with a companion star, still burning, still fat with gas. Over centuries, the white dwarf pulls at that companion, siphoning off a thin stream of matter, drawing it in and adding it to its own mass, one sip at a time. This goes on for a long time. The white dwarf gets heavier and heavier. Gravity keeps packing more and more matter into a body was never built to hold this much. There is a line it cannot cross, a precise mass, the same in every case, everywhere in the universe. The moment the white dwarf's mass creeps up to that threshold, the whole star ignites in a runaway nuclear reaction and tears itself apart. This is a type Ia supernova, and for a few weeks it can outshine every other star in its galaxy combined. Here is the gift buried inside that violence. Because the threshold is always the same, the explosion carries almost exactly the same true brightness, no matter which galaxy it happens in, no matter how old the star was, no matter how far away it sits. A candle that always burns at the same wattage, scattered across billions of light years. Astronomers call this a standard candle, and it is the reason these explosions became one of the most valuable tools in the entire distance ladder. Cepheids run out of range after a certain distance. Supernovae keep working almost to the edge of what we can see. In the late 1990 seconds, two teams pointed this tool at distant galaxies, expecting to measure how quickly the universe's expansion was slowing down, because everyone assumed gravity had to be winning that fight eventually. The supernovae came back fainter than they should have been if that were true. Fainter meant farther away than expected. Farther away than expected meant the expansion was not slowing at all. It was speeding up. That discovery reshaped cosmology overnight and earned its discoverers the Nobel Prize a few years later, handing science a new mystery it still hasn't solved. Dark energy, the invisible force apparently responsible for that acceleration. But before any of that could happen, someone had to calibrate the candle in the first place. This is where the ladder actually connects. Astronomers hunt for the rare galaxy that happens to contain both a population of Cepheid variables and a recent Type Ia supernova in the same neighborhood. The Cepheids, using Leavitt's rule, hand over a distance. That distance lets astronomers work out exactly how bright the supernova truly was, since they now know how far its light had to travel to look as faint as it did. Once that true brightness is nailed down across enough of these paired galaxies, supernovae can be trusted on their own. No Cepheid required, reaching out to distances that pulsing stars could never touch. This is the exact chain that carries the distance ladder out to where the Hubble constant of 73 finally gets measured. And it has been attacked from every angle you'd expect. What if dust between us and the supernova dims it unevenly, throwing off the calibration? What if a star's chemical makeup, different in an old galaxy than a young one, changes how the explosion actually burns? What if the threshold that triggers detonation isn't quite as fixed as assumed, varying slightly from star to star in ways that would poison the whole method? Every one of these objections has been tested directly against the data. So far, every one of them has held up. The person who ended up owning this number is a scientist named Adam Rees, and he came to it already carrying a Nobel Prize. He won it in 2011, part of the team that found the universe's expansion were speeding up rather than slowing down. That discovery alone would have been enough for most careers. Rice turned around and spent the next 2 decades chasing an even harder problem, leading a collaboration that goes by the name SH0ES. The work itself is not glamorous. It is grinding, repetitive, and demands a kind of patience most people don't have. Somewhere out there are galaxies that happen to contain both a healthy population of Cepheid variables and a Type Ia supernova, recent enough to still be visible. Those galaxies are rare. Finding them means combing through catalogs, checking survey after survey, waiting for the universe to hand you a galaxy with both ingredients present at once. Once you find one, the work is only beginning. Cepheids need to be watched across multiple full pulse cycles, sometimes weeks or months long, to nail down their rhythm precisely enough to trust. That means hundreds of hours of telescope time, spread across years, pointed at a small handful of galaxies scattered across the sky. To understand how far this has come, it helps to look back at where it started. Hubble's original estimate that night at Mount Wilson was off by a factor of 7, not 7%. 7 times too high. For decades after him, the number kept swinging wildly between different research groups, sometimes disagreeing by a factor of 2. Even by the year 2000, with better telescopes and better methods, the uncertainty still sat around 20%. Anyone working in cosmology at the time would have told you a 20% uncertainty was simply the cost of doing business, the best anyone could hope for given the tools available. That is not a small improvement. That is the difference between a rough guess and a measurement precise enough to build a career-ending argument on, and the number that precision keeps landing on, release after release, is 73.04. Here is what makes this genuinely strange. Every single time, SH0ES has published an updated result, tightening their error bars further. The expectation across the field was the same. Surely this next release brings the number down, closer to the 67.4 the early universe side keeps insisting on. Surely this is the year the gap finally starts closing. It never has. Each new release has landed almost exactly where the last one did, just with a smaller margin of error wrapped around it. The number is not drifting toward agreement. It is hardening in place. Every objection anyone has thrown at this result has gone through the ringer. Dust dimming the Cepheids unevenly? Tested, corrected for, accounted for. Differences in a star's chemical makeup, its metallicity, subtly shifting the brightness to pulse relationship from one galaxy to the next, tested. Stellar crowding, where a Cepheid's light blurs together with a fainter neighbor and throws off the measurement. Tested directly, repeatedly, using every trick available to separate the signal from the noise. And after all of it, the number has not moved. 73.04 sits there, precise to about 1%, refusing every excuse offered to make it go away. Every number in this story so far has come from measuring something recent. Nearby stars. Nearby explosions. Galaxies close enough, cosmically speaking, to watch in real time. But there is a third kind of light in this universe, older than any of that, and it comes from a moment so far back that stars themselves did not exist yet. For the first 380,000 years after the Big Bang, the universe was not a place light could travel through. It was a hot, dense fog, electrons and protons and photons all packed together so tightly that light could not move more than a fraction of an inch before it slammed into a charged particle and scattered. Photons were born, absorbed, born again, absorbed again, trapped in an endless bounce, going nowhere. If you had somehow existed inside that fog with a flashlight, the beam would have gone nowhere. It would have vanished into the crowd within a heartbeat. Then, at 380,000 years, the universe cooled just enough for something to change. Electrons slowed down enough to be captured by protons, forming the first stable atoms. The instant that happened, the fog cleared. All at once, everywhere, photons that had been trapped for hundreds of thousands of years suddenly had nothing left to bounce off of. They shot outward in every direction, free for the first time, and they have been traveling ever since. That light is still arriving. Right now, it is the oldest light that exists anywhere, and we call it the cosmic microwave background. Nobody set out to find it. In 1965, 2 engineers at Bell Labs in New Jersey were working with a large horn-shaped antenna, trying to track down a source of radio static that kept showing up in their equipment. No matter which direction they pointed the antenna, the hiss was there. They checked the wiring. They checked for interference from nearby cities. At one point, they climbed inside the antenna itself and scraped out what turned out to be pigeon droppings, convinced that was the culprit. The hiss stayed exactly the same. It didn't matter what direction they aimed, what time of day it was, what season. The static came from everywhere at once, at the same steady strength, and nothing they tried could make it go away. What they had stumbled onto, without meaning to, was the leftover light from the birth of the universe itself. The photons that broke free the moment the fog cleared, stretched now by billions of years of cosmic expansion into faint microwave radiation, arriving equally from every direction in the sky, because that is exactly what you would expect from light released everywhere at once, an unimaginably long time ago. Here is what makes this ancient light worth more than just a historical curiosity. It isn't perfectly uniform. Scattered across it are tiny temperature variations, differences of about 1 part in 100,000. Patches slightly warmer or slightly cooler than their surroundings. Those variations, anchored into that pattern, is the exact recipe the early universe was built from. How much ordinary matter existed, how much invisible dark matter, how much dark energy, and how fast space itself was stretching in that first fraction of cosmic history. This is the part that turns an old photograph into a working tool. Because if you can read that recipe accurately, you are no longer just looking at a picture of the infinite universe. You can run the physics forward. You can take those exact ingredients, plug them into the equations that govern how space behaves, and calculate from first principles exactly how fast the universe should be expanding today, without ever pointing a telescope at a single nearby galaxy. That calculation is where the other half of this crisis comes from. To turn that ancient light into a working number, scientists needed a way to see it clearly without the blur of our own atmosphere getting in the way. So in 2009, a satellite named Planck launched off the coast of French Guiana and drifted out to a stable point in space over 1 million miles from Earth, far enough from our planet's heat and radio noise to listen to the sky without interference. For more than 4 years, it sat out there scanning the entire heavens, slowly building the most detailed map ever made of the cosmic microwave background. The result looks strange at first glance. A speckled oval, flattened out like a projection of the whole sky, covered in patches of color that shift from deep blue to fiery red. Those colors aren't decoration. Each one marks a temperature difference of roughly 1 part in 100,000, a variation so small it would be meaningless in almost any other context. But here, each tiny blotch is a fossil, It records exactly how matter was distributed across the universe at the moment that ancient light broke free, back when the entire cosmos was younger than a single human lifetime is long, measured against everything that came after. Here is where the map stops being a picture and starts being a tool. Cosmologists take this pattern of splotches and feed it into a mathematical model of the universe, a model built from a set of assumptions about how much ordinary matter exists, how much dark matter, how much dark energy, how curved or flat space is. They adjust those assumptions, run the model, compare the output against Planck's actual map, adjust again, and repeat, over and over, until the model's predictions line up with what the satellite actually recorded. Once that match is locked in, the model isn't just describing the past anymore. It becomes a machine you can run forward. Scientists take that tune model, let it play out across 13.8 billion years of cosmic history, tracking how the ingredients baked into that early recipe should behave as the universe ages, right up until today. Run that machine to the present moment, and it spits out a number for how fast space should be expanding right now, calculated entirely from a snapshot taken almost 14 billion years ago. That number comes out to roughly 67.4, with an uncertainty under 1%. And this is not a result that came from one satellite working alone in a vacuum, easy to dismiss as a fluke of one instrument's quirks. Other experiments, built with entirely different hardware, pointed at the same ancient light from different locations, have landed on essentially the same answer. Ground-based telescopes high in the Chilean desert. Instruments parked at the South Pole. Different engineers, different funding sources, different decades of design work, and they all keep converging on the same number Planck found staring at the sky from 1 million miles out. This is the collision worth sitting with for a moment. This 67.4 is not some rushed estimate, not a sloppy guess thrown together by a team in a hurry. It is one of the most carefully constructed values in the history of science, built from 4 years of continuous observation, cross-checked by independent instruments using completely different methods, verified again and again by teams who have every incentive to find each other's mistakes. And it will not agree with the number sitting on the other side of this story. 2 values, both earned through years of exacting work, both defended by scientists who have staked their reputations on getting it right. They cannot both be describing the same universe the way we think they are. Scientists have a specific way of talking about how much to trust a disagreement like this, and it comes down to a single word, sigma. Sigma measures how likely it is that a gap between 2 results is just random noise, the kind of static that shows up in any measurement if you take it enough times. A small gap, 1 sigma or so, barely raises an eyebrow. That's the normal wobble you'd expect, even if both teams were measuring the exact same true value. Push past 3 sigma, and people start paying attention. Physics doesn't call something a real discovery, though, until it clears 5 sigma. That's the bar. Below it, you might have something. Above it, you have a fact. The Hubble tension sits at roughly 5 sigma right now. In some analyses, climbs even higher. That number puts it in the same territory as the confirmation of the Higgs boson, the discovery that took decades of collision data at the Large Hadron Collider before physicists were willing to stand up and call it real. This is not a maybe. This is not a rounding artifact that a slightly better telescope will quietly smooth away. Statistically speaking, this gap has already crossed the same threshold that lets scientists announce, without hedging, that they had found a new particle. So where does that leave the field? Honestly, there are only 3 possibilities on the table, and none of them are comfortable. The first is that SH0ES has a hidden flaw somewhere in the ladder, some systematic error that keeps slipping past every check thrown at it. The second is that Planck has a hidden flaw instead, some subtle problem in how the ancient light gets translated into a prediction for today. The third possibility is the one that unsettles people the most. Both teams are right, both numbers are accurate for what they're measuring, and something genuinely changed between the early universe and the late universe that our current physics simply doesn't have a place for yet. To feel how strange a 9% gap actually is, think about something ordinary. If your grocery bill came out 9% higher than the receipt should say, you might not even notice. Maybe you'd shrug it off as inflation. Nobody would call the local news. A 9% difference in daily life barely registers. Now put that same 9% onto the expansion rate of the entire universe, the number that sets the age of everything, the size of everything, the fate of everything. That same small percentage stops being a shrug. It becomes a canyon. It is the difference between a universe that is 13.8 billion years old and one that is closer to 12.6. It is the difference between models that fit cleanly and models that don't fit at all. Here is the shape of the problem as it stands today. 90% of cosmology fits together beautifully. The physics of the early universe, the physics of galaxies, the physics of light traveling across billions of years. Almost all of it locks into place with stunning precision. But that last 10%, the piece that would let the early number and the late number finally shake hands, refuses to click. Scientists have rotated it, flipped it, tried it from every angle they can think of. It still won't fit. And a puzzle with one piece that won't seat, no matter how you turn it, isn't a puzzle with a defect in the piece. It's a puzzle telling you the picture on the box might be wrong. For years, a lot of scientists quietly held on to one hope. Somewhere in that ladder, a mistake was waiting to be found, and the right telescope would finally dig it out. The James Webb Space Telescope was supposed to be that telescope. Its infrared vision cuts through dust in a way Hubble never could. Dust had always been one of the favorite suspects in this case. If dust inside those distant galaxies was quietly dimming the Cepheids, feeding false brightness readings into the calculations, that alone could explain why the local number kept coming in high. Webb, with its sharper eyes tuned to exactly the wavelengths that dust struggles to block, was the instrument built to catch that kind of error if it existed. Rios knew this. So did every scientist, hoping the tension would turn out to be nothing more than a solvable technical glitch. So Rios's team did the obvious thing. They pointed Webb straight at the same galaxies SH0ES had already measured with Hubble, the same Cepheids, the same pulsing stars that had built the ladder up to 73.04 in the first place. They retested the pulse relationships from scratch, watching the same rhythms Leavitt had first mapped out over a century earlier. They checked, specifically and carefully, for stellar crowding. That was the other leading suspect. If a Cepheids light had been quietly blurring together with some fainter, unresolved neighbor in Hubble's older, less sharp images, Webb's superior resolution should catch it and pull the two apart. The result came back plainly. No hedging, no asterisk buried in a footnote. Webb confirmed SH0ES. The Cepheids weren't hiding behind dust. They weren't blurred together with hidden neighbors, throwing off the brightness readings. When Webb looked at exactly the same stars with exactly the sharpest tool humanity has ever built for this job, it saw the same brightness, the same pulse, the same distance Hubble had already reported. The local number did not move. Not down, not towards 67.4, not by any amount. This is the part that mattered more than the number itself. Before Webb's confirmation, there was still a clean, comfortable way out of this entire mess. Somebody just needs a better telescope. Better resolution, better dust correction. The problem is instrumental, and instruments improve. That was always on the table as the easy answer. Webb took that answer off the table. With instrument error effectively ruled out, only 2 doors were left standing open. Either there is still some deeper, systematic hiding somewhere in the ladder, something nobody has thought to check yet, buried underneath every calibration step, from parallax all the way up to the supernovae. Or the discrepancy is real, and it is telling us something true about the universe that current physics simply does not have room for. That is not a comfortable place for a field to land. And you can hear it in how the language around this problem started to shift. Before Webb's confirmation, most scientists used the word tension. Tension is a word that implies something temporary, something under strain but fixable. The kind of disagreement that eventually resolves once someone finds the missing piece. After Webb pointed its mirror at those same Cepheids and came back with the same stubborn answer, that word started to feel too soft for what people were actually looking at. This was the moment the mood in the field genuinely changed. Not because of one dramatic press conference, but because the safest possible resolution had just been eliminated by the most powerful telescope ever built. What was left wasn't a technical hiccup anymore. It was starting to look structural. And structural problems don't get called tensions for very long. That shift found its clearest voice in January 2025, when a scientist named Dan Skolnick stood in front of a room full of colleagues at the American Astronomical Society meeting and said the sentence a lot of people had been avoiding. The Hubble tension, he told them, is not a tension anymore. It's a crisis. That is not a casual swap of vocabulary. Words carry weight in a room full of physicists, and these 2 words carry very different implications. Tension suggests strain that resolves itself once you find the right fix, the way a rope goes slack again, once you finally locate the snag. Crisis suggests something has already broken, and there may be no small fix waiting to be found. One word describes a puzzle. The other describes a structure that no longer holds together the way it's supposed to. Skolnick did not just stand up and reach for the more dramatic word out of frustration. He came with a new number. His team had gone looking for a fresh anchor point, one that could sidestep the entire argument raging around Cepheids and dust and stellar crowding. They found it close to home, in the Coma Cluster, a dense gathering of galaxies that has been studied so thoroughly for so long by so many independent groups that its distance is about as well pinned down as any object in the sky. You don't need a single pulsing star to know how far away Coma sits. You already have that number, confirmed from several completely separate directions. Using that cluster as a starting rung, Skolnick's team calculated a fresh value for the expansion rate. It came out to 73.5. Here is why that number matters more than its digits suggest. Every argument up to this point about the local measurement has circled back to Cepheids, because Cepheids are the foundation SH0ES stands on, and Cepheids come loaded with legitimate technical worries, dust crowding, subtle contamination from neighboring stars. Skeptics have had a specific, named target to aim their doubts at for years. Anchor your measurement in the Coma Cluster instead, and that entire target disappears. There are no Cepheids to distrust here. no pulse rhythms to second guess. Just a well-established distance to a nearby cluster, built from methods that have nothing to do with the stars Leavitt first studied over a century ago. The number that came out the other end landed right back in the same high territory SH0ES had already staked out. Not close to 67.4, not splitting the difference, sitting comfortably up near 73, arrived at through a completely different route than the one everyone had spent years arguing about. This is the pattern that should stop you. It is not that one team keeps getting a high number using one method that might carry a hidden flaw. It is that every fresh, independent way of measuring the local universe keeps landing in that same high neighborhood, using different stars, different clusters, different calibration chains that share almost nothing with each other. Meanwhile, every fresh look at the early universe, using entirely different instruments than Planck, keeps landing back down near 67. Nothing shows up in between. No result splits the difference. No new method lands 70 and quietly resolves the argument. The two camps keep hardening in place, each one collecting its own independent evidence, and the space between them stays exactly as wide as it's ever been. Stand in the middle of a flat desert sometime and take the temperature. It reads normal. Warm, dry, exactly what you'd expect. Nothing about the reading feels wrong. Now imagine someone tells you that just past the horizon, in every direction, the rest of the planet is jungle. Thick, humid, dense with life. Your thermometer wasn't broken. It told you the truth about where you were standing. You simply happened to be standing somewhere unusual, and you had no way of knowing that from inside the desert alone. Something close to that might be happening to us, and it starts with a discovery from 2013. 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, set out to count galaxies. Not nearby ones you could see with an ordinary telescope, but faint infrared light from galaxies scattered across our cosmic neighborhood, the kind of survey that takes patience, the telescope built to catch light most instruments miss. They expected the count to come back roughly even in every direction, the way you'd expect grains of sand to be spread evenly across a beach. Instead, they found a hole. A region stretching nearly 2 billion light-years across, where galaxies sit anywhere from 10 to 50% less dense than the average found elsewhere in the universe. They called it the KBC void, using the first letters of their own names, though you'll also hear it called the local hole, which is a more honest description of what it actually is. And the implication sitting inside that name is almost too large to say plainly the first time. Earth may not be floating in an ordinary patch of cosmic space at all. We may be sitting near the center of the largest known emptiness in the entire observable universe. To feel the size of that, picture the observable universe as the Pacific Ocean, edge to edge. The KBC void, dropped onto that same scale, would be a circle wide enough to swallow most of North America. That is not a gap in the data. That is not a rounding artifact from a survey that missed a few galaxies. That is a structure large enough to reshape how you think about where you live. Here is why a hole like this would matter for everything we've measured so far. Gravity does not sit still and wait. Regions of the universe with more matter in them pull harder than regions with less. If we are living inside a large, underdense bubble, surrounded on all sides by denser regions further out, then the matter in those denser surroundings is tugging on everything inside our bubble, pulling it gently outward toward the walls of the void and away from the center. From where we stand, every galaxy nearby would appear to be receding a little faster than it actually is, not because space itself is stretching any quicker, but because gravity from outside the void is giving every galaxy an extra shove in the same direction we're already looking. That added shove would land directly on top of the real expansion rate, inflating the local number without anyone realizing the inflation was there. If that mechanism is real, it would explain the whole shape of the discrepancy. The early universe measurement doesn't care about our particular neighborhood. It's an average taken over the entire sky, but the local measurement is built entirely from galaxies close enough to sit inside our unusual pocket of emptiness, which means it could be reading out a number biased by exactly where we happen to be standing. There's a catch buried inside that explanation though, and it's not a small one. The standard model of cosmology has a rough estimate for how often a void this size should form, given how much time the universe has had. That estimate comes out to something like 1 in a billion, which leaves two uncomfortable choices sitting side by side. Either we are living through an extraordinary statistical fluke, a void so improbable it should barely exist anywhere in the entire universe, or the model itself, the one making that 1 in a billion prediction, is missing something it was never built to account for. Whatever is causing that void, or whatever is causing the gap alongside it, both explanations eventually run into the same suspect: dark energy. Roughly 70% of everything that exists is made of it, and nobody has ever seen it, touched it, or caught it in an instrument built to detect matter directly. It doesn't clump, it doesn't shine. The only reason we know it's there at all is that space keeps stretching apart faster than gravity alone should allow, and something has to be doing the pushing. For decades, physicists treated that push as fixed. Einstein had actually written something close to it into his own equations first, a term he called the cosmological constant, added purely to keep his math from predicting a universe that moved. When Hubble later proved the universe was expanding after all, Einstein dropped the term and called it his worst mistake, but the idea didn't die. It came back decades later, once the acceleration itself was discovered, and this time it stuck. Dark energy became the modern version of that constant, a fixed number baked permanently into the fabric of space, pushing at exactly the same strength yesterday, today, and a billion years from now. That assumption sat underneath nearly every calculation in cosmology for a generation. Then a machine on a mountain in Arizona started collecting data that didn't match the assumption at all. The instrument is called DZII, the Dark Energy Spectroscopic Instrument, and it works nothing like a normal telescope, pointed patiently at one target. It carries 5,000 tiny robotic positioners, each one capable of aiming its own fiber optic eye at a different galaxy at the same moment, capturing thousands of light signatures in a single exposure. Over 3 years, Delaware SI used that swarm of robotic eyes to map the positions of nearly 15 million galaxies, building the largest three-dimensional map of the cosmos ever assembled, stretching back across roughly 11 billion years of cosmic history. In March of 2025, the team released what that map actually showed, and it wasn't what anyone had built the instrument expecting to find. Dark energy's influence across that 11 billion year stretch does not look like a fixed number holding steady the whole time. It looks like it is losing strength. Not collapsing overnight, not vanishing, but trending downward, the push measurably weaker now than it appears to have been earlier in cosmic history. One cosmologist working with the data put it in words simple enough to sit with. Dark energy has gone from pushy to tired. That is not a small correction to a decimal point somewhere in a textbook. If that trend holds up under further scrutiny, it means the central assumption underneath most of modern cosmology, the idea that dark energy is a constant, was wrong the entire time. Every calculation that treated it as fixed, including the very model Planck used to arrive at 67.4 in the first place, was built on a piece of ground that isn't actually solid. Cosmologists haven't just been arguing about the wrong number. They may have been standing on the wrong foundation while doing it. There's a spring on the back of most screen doors. Pull it open, and the spring pulls back. The farther you stretch it, the harder it resists, until it drags the door shut the second you let go. That's gravity in a single object you can hold in your hand. It always pulls back, it never pushes. Now imagine a spring that breaks that rule entirely. Stretch it, and instead of resisting, it shoves harder the more you pull. Let go, and it doesn't snap back. It keeps pushing outward faster the farther it goes. That's the picture physicists have been using for dark energy since the moment they accepted it was real. Space stretches, and whatever dark energy is, it pushes back against that stretching in the wrong direction, adding force rather than resisting it. And the more space there is, the harder it pushes. For a long time, that was treated as the whole story. One spring, one behavior, forever. But once cosmologists started taking seriously the idea that dark energy might change over time, they needed language for what kind of change was even possible. Two names came out of that work, and they describe two very different futures. The gentle version is called quintessence. In this picture, dark energy still pushes outward, still drives that acceleration, but the strength of the push fades as time goes on. The universe keeps expanding, keeps drifting apart, but it does so more calmly with each passing era. Nothing gets torn, nothing snaps. It's a slow exhale stretched across billions of years. The other version has no gentleness in it at all. Physicists call it phantom dark energy, and unlike quintessence, it grows stronger the longer the universe expands. Not weaker, stronger. Feed it more space, it pushes back with more force than before, an escalation that has no natural ceiling. Run that forward far enough, and the acceleration stops being something galaxies drift apart under. It becomes something violent. Galaxy clusters get torn from each other first, then individual galaxies, then solar systems, then the atoms holding matter together. Physicists have a name for that ending too. They call it. Here's where the 2025 data got uncomfortable. When researchers combined DSE's galaxy map with the cosmic microwave background and the full supernova catalog, the fit that came back split cleanly down the middle of cosmic history. Early universe constraints lean toward that phantom behavior. Dark energy acting stronger than a constant should, back when the cosmos was young. Late universe constraints leaned the other way entirely, toward the quintessence side. Dark energy behaving as though it's been losing steam. Sit with what that actually implies. It isn't that dark energy has always been a phantom or always been quintessence, and we simply measured it wrong on one end. It's that the data is describing something that acted like one thing early on and something close to the opposite later. A switch, sometime in the middle of cosmic history. Nothing in the standard model has a slot for that. A cosmological constant is called constant because it's supposed to be one fixed number, unchanging, the same in every era you check it. It was never built to have moods. It was never built to have phases at all. The fact that the data appears to demand exactly that a force that shifts its own personality across billions of years, is not a small patch waiting to be bolted onto the old model. It's the kind of finding that starts forcing physicists to invent categories nobody had written down before. A researcher named Young-Wook Lee went back through decades of supernova data with a question most of the field had already stopped asking. Everyone assumed the acceleration story was settled. Lee's fresh analysis suggested it might not be. His work points toward a universe whose expansion has already peaked and is now sliding into a slower phase, not speeding up further, but easing off, the way a car's engine backs off once it's carried you up a hill. Here's a picture that makes the shape of that claim easy to hold on to. Throw a ball straight up and watch what happens to it. The instant it leaves your hand, gravity starts pulling back, slowing the climb second by second. That's the early universe. Gravity had the upper hand for billions of years, dragging on the expansion, trying to pull everything back together after the initial outward rush. Then, around 5 or 6 billion years ago, dark energy took over, and the ball that should have kept slowing down got shoved upward instead, faster than gravity alone could explain. That's the acceleration astronomers found in the late 1990 seconds, the discovery that rewrote the whole field. Lee's analysis suggests we might be watching a third act now. If dark energy really is weakening, the way the DESI data hints at, then gravity doesn't disappear just because dark energy showed up. It's still there, still pulling, patiently waiting for its moment. In this view, that moment may already be arriving. The ball that got thrown upward by dark energy's shove could be running out of push, and gravity might be starting to win the argument back. None of this counts as settled. Different teams running different analysis methods on overlapping data have come back with different verdicts. Some confirm continued acceleration, no slowdown in sight, the standard picture intact. Others, using methods closer to Lee's, find hints of exactly the deceleration he's describing. Right now, the field doesn't have a consensus. It has two competing readings of the same sky, and neither side has enough weight behind it to call the argument closed. It's worth sitting with why this particular disagreement matters more than most technical disputes buried inside cosmology papers. This isn't an argument over a decimal point that only specialists would care about. Continued acceleration means galaxies keep drifting apart forever, the sky emptying out slowly across trillions of years, ending in a cold, isolated universe where nothing new can ever happen again. Deceleration means something else entirely. It means the expansion eventually stalls, reverses, and the universe begins pulling itself back together, heading toward contraction instead of isolation. These aren't two abstract categories sitting in a textbook waiting to be picked based on which model looks tidier. They are literally the two possible endings for everything that exists, including whatever comes after us. Nobody is going to settle that argument with a single new data release. But the instruments capable of sharpening this picture are already active, or about to be. DESI keeps expanding its galaxy catalog, adding more data every year that Lee's method and its rivals can be tested against. Euclid is now mapping the shapes and positions of galaxies across a huge stretch of sky, built specifically to catch signs of exactly this kind of shift. And the Roman Space Telescope, once it's running, will add another independent set of eyes to the same question. Within the next several years, this particular argument should stop being a matter of which analysis you trust and start being a matter of what the sky actually says. Every explanation so far still keeps dark energy on the table. The void might inflate our local reading, the DESI data might mean the push is fading. But nobody so far has suggested the push was never there in the first place. That's exactly what a physicist named David Wiltshire, working at the University of Canterbury in New Zealand, has spent years arguing. His claim isn't that dark energy behaves strangely. His claim is that dark energy may not exist at all. What Wiltshire proposes instead is almost unsettling in how simple it sounds once you hear it. The acceleration everyone has been measuring, the thing that won a Nobel Prize, the thing DESI just spent 3 years mapping across 15 million galaxies, might not be a force pushing space apart at all. It might be something happening to time itself, specifically time flowing at different rates in different parts of the universe, in a way standard cosmology never bothered to account for, and that uneven flow getting mistaken for a mysterious form of energy that doesn't exist. This isn't speculation about exotic new physics nobody has ever tested. It rests on something already proven, already running in your pocket right now. Einstein's general relativity says gravity slows time. Stronger gravity, slower clock. That effect isn't theoretical. GPS satellites orbit Earth in weaker gravity than we experience on the ground, which means their onboard clocks tick very slightly faster than clocks down here. If engineers didn't correct for that difference constantly, your phone's location would drift off by miles within a single day. That correction runs every day on every satellite because the effect is real and it is measurable. Wiltshire's argument scales that same effect up from a satellite a few hundred miles overhead to the largest structures in the cosmos. Picture a clock sitting deep inside a dense cluster of galaxies surrounded by enormous gravitational pull. Now, picture a second clock floating out in one of the vast, nearly empty voids scattered across the universe. Barely any mass around it at all. Gravity there is weaker. According to the same physics already confirmed by satellites overhead, that second clock should run faster. Not by much in any single second. But multiply that tiny difference across 13.8 billion years, and it stops being tiny. It becomes a gap large enough to matter. Here is where Wiltshire's model actually breaks from everything else in this story. Standard cosmology treats the universe as though one single clock could describe all of it. A single average time, flowing evenly everywhere, regions smoothed together as though the lumps and voids and clusters didn't matter. Wiltshire says that averaging is exactly where the illusion creeps in. If you take regions ticking at different rates, dense clusters running slow, empty voids running fast, and then blend them into one number the way standard models do, the math produces something that looks exactly like acceleration. Not because space is actually being pushed apart faster and faster, because the clocks doing the measuring were never running at the same speed to begin with. That is the entire core of what's called the timescape model. No dark energy, no invisible force, no cosmological constant. Just an honest accounting of time flowing unevenly across a universe that was never smooth in the first place, mistaken for decades as evidence of something pushing from outside. For a long time this sat at the edge of the field, interesting but unproven. That changed with a recent analysis using the Pantheon plus supernova catalog, the same kind of exploding star data that anchors so much of standard cosmology. Run through Wiltshire's framework, that data favored the timescape model over standard dark energy at a 99% confidence level in at least one published study. That is not a fringe result anymore. That is a number serious enough that the rest of the field can no longer look away from it. A claim like that doesn't get to stay theoretical for long. If timescape is right, It has to make predictions that can be checked against the sky, not just retrofitted to explain data that already exists. And it does. Think about driving across a stretch of highway where the speed limit keeps changing. 20 miles at 60, then a construction zone drops you to 30. Then it opens back up to 70 for the next stretch. If someone stood at the far end of your trip with nothing but a stopwatch and the total distance covered, they could only calculate your average speed across the whole drive. That average might come out to 50. But you were never actually going 50 at any point. You were speeding up and slowing down constantly. And a single average number would hide every bit of that. Worse, if that observer assumed you'd been driving at a steady speed the whole way, and then noticed the average crept up compared to a previous trip, they might conclude you'd been accelerating, when really you just spent more time in the faster zones this time around. That is the exact trap Wiltshire says standard cosmology has fallen into, except the zones aren't stretches of highway, they're voids and clusters. In his model, voids expand faster because gravity out there is weaker, nothing much around to hold the stretching back. Clusters expand slower, dragged on by all that surrounding mass. Light traveling from a distant galaxy to us doesn't pass through one zone or the other. It crosses through both, picking up the fingerprint of every void it skims, and every cluster it grazes along the way. By the time that light reaches a telescope on Earth, it's carrying a blended signal, and if you assume the whole trip happened at one uniform rate, you'll read acceleration into a pattern that was really just uneven terrain the whole time. The numbers behind this aren't small enough to wave away. Under Wiltshire's calculations, a clock sitting inside the Milky Way, deep in our own gravitational well, may run something like 35% slower than a clock parked out in a typical void. That is not a rounding difference. That's the kind of gap that, stretched across billions of years, reshapes how you'd interpret almost any measurement taken from inside a cluster like ours. Here's the part that keeps this from being just an interesting story, with no way to check it. Timescape doesn't only explain the past, it makes a specific forecast about what surveys should find if you look in the right place. The model predicts that the local Hubble flow, the pattern of nearby galaxies receding from us, should show more scatter than the standard picture allows, and that scatter shouldn't be random. It should depend on direction, showing up most clearly on scale somewhere between 30 and 100 megaparsecs, exactly the range where voids and clusters are large enough to leave their mark, but close enough for us to map in detail. That is a number you can go check, not a philosophy. A measurement waiting to be taken. Two instruments are built to take it. Euclid is already collecting the kind of wide-field data that could reveal whether that direction-dependent scatter is really there, at the scale Wiltshire's model demands. The Roman Space Telescope, once it comes online, adds another independent set of eyes aimed at the same question. Neither mission was designed around Timescape specifically, but both happen to be exactly the tools capable of confirming it, or quietly ruling it out for good. There's a rule sitting underneath every model cosmologist build, so basic, it rarely gets a second thought. Zoom out far enough, and the universe should look the same, no matter which way you point your telescope. Not identical in every detail, but even in its overall texture, the way pepper sprinkled across a tablecloth looks roughly the same density whether you're staring at the corner or the center. No special direction, no preferred spot. Just a uniform scatter once you step back far enough to stop noticing individual grains. For most of the 20th century, that rule held up without much argument. The clearest proof came from the cosmic microwave background itself, that ancient light from 380,000 years after the Big Bang. Map it across the entire sky, and it comes back almost perfectly uniform. The same faint temperature in every direction you check, aside from those tiny ripples already built into the story. It was about as clean a confirmation as physics gets. The universe, at its largest scale, behaved exactly the way the rules said it should. Then better surveys started finding things that don't fit inside a tablecloth, sprinkled evenly with pepper. Start with the Sloan Great Wall, a structure of galaxies strung together across more than 1 billion light-years, filaments of matter linked into something too large to call a cluster or even a supercluster. Move further out, and you hit something even harder to explain. The Hercules Corona Borealis Great Wall, a formation stretching nearly 10 billion light-years across. That's not a typo worth double-checking. 10 billion light-years is close to 1/4 of the entire observable universe, wrapped into one connected structure. Here's where the math turns uncomfortable. The universe is roughly 13.8 billion years old. Gravity is patient, but it isn't magic, and pulling matter together into something that size, using nothing but the slow accumulation of gravitational attraction over cosmic time, doesn't add up. There hasn't been enough time for gravity alone to build something on that scale. Not according to the same standard model that gave us 67.4 on one side of this story and 73 on the other. Then there's a separate anomaly, quieter than a wall of galaxies, but just as strange once you sit with it. Quasars, the blazing cores of distant galaxies powered by feeding black holes, should scatter evenly across the sky the same way everything else is supposed to. Under this rule, they don't. Careful surveys have found a slight excess of quasars bunched in one direction, and a corresponding deficit in the opposite direction. A lopsidedness that shouldn't exist if the universe really treats every direction the same. None of these findings, taken alone, forces anyone to throw out a foundational rule. A wall of galaxies could be an unlikely but possible fluke. A slight quasar imbalance could be a statistical wrinkle that smooths out with more data. Voids, walls, dipoles, each one survivable in isolation. Each one explainable away with enough caveats attached. But they aren't isolated. Stack the KBC void against the Great Walls. Stack the quasar dipole against a Hubble constant that splits cleanly into two camps depending on when you're measuring rather than where. Individually, coincidences. Together, they start sketching the outline of something structural. A universe that may not sit as evenly as the rule requires, and a set of mismatched expansion numbers that might be symptoms of that same unevenness rather than separate problems entirely. Every fix so far has aimed at the late universe, at voids or fading dark energy, or clocks running unevenly across cosmic structure. There's a different family of solutions that goes after the other end of the timeline entirely, back to the first sliver of cosmic history, so early that most people never think to look there for an answer. The idea is called early dark energy, and the name is almost a warning label for what it proposes. A force behaving something like dark energy, pushing space outward, may have briefly existed in the first 10,000 to 100,000 years after the Big Bang, not the dark energy we measure today. A separate, temporary version that showed up early, did its work, and then vanished completely, leaving no trace except the fingerprint it left behind in the structure of the cosmos. To understand why that fingerprint matters, you need to picture something physicists call the sound horizon. In the hot, dense plasma filling the early universe, sound waves rippled outward the same way ripples spread across a pond, except these waves were made of pressure, moving through plasma rather than water moving across a surface. When the universe cooled enough for atoms to form, and that plasma turned transparent, those ripples froze in place, locked into the pattern of matter scattered across space. That frozen pattern works like a ruler, a fixed, known length baked into the early universe that scientists can measure in the cosmic microwave background and use to calibrate distances across the rest of cosmic history. Planck's entire calculation of 67.4 depends on knowing exactly how long that ruler is. Here's the mechanism early dark energy would introduce. If that temporary push was real, it would have shoved space outward during the exact window when those sound waves were still rippling, which means the ruler that eventually froze in place would have ended up shorter than standard physics assumes. And a shorter ruler changes everything downstream of it. Feed a smaller sound horizon into the same calculation that produced 67.4. And the math pushes the answer higher, closer to the number SH0ES has been defending with Cepheids and supernovae. This idea picked up serious momentum in 2024 when a team of researchers at MIT ran the numbers on exactly this scenario. What they found wasn't just a fix for the sound horizon problem. Adding early dark energy into their models also boosted how quickly structure could form in the infant universe, which mattered because Webb had already been finding galaxies far too massive and fully formed for how young the cosmos was supposed to be at that point. One mechanism, briefly switched on and then gone, appeared to ease the Hubble tension and explain Webb's impossibly early galaxies at the same time. That's the appeal. It's also where the honesty has to come in. Nobody has identified what physical field would actually produce early dark energy. There's no particle waiting in a detector somewhere. No confirmed mechanism borrowed from known physics that behaves this way. It's a patch built to fit the shape of the problem, not a discovery pulled independently out of an experiment. And when researchers add it into their models, it doesn't only fix things, it tends to throw off how galaxies cluster later in cosmic history, creating a new mismatch even as it resolves the old one. That trade-off is exactly why the idea hasn't been dropped. Early dark energy remains one of the most actively pursued fixes in the entire field, not because anyone has proven it real, but because it's rare to find a single mechanism that reaches backward and solves two separate crises. Unproven, and still, nobody's willing to walk away from it yet. Standard cosmology made a quiet, confident prediction about what the universe should have looked like 300 million years after the Big Bang. Small galaxies. Half-built structures still gathering themselves out of gas and dark matter, the way a city starts as a scatter of tents before it has streets or skylines. Prediction wasn't a guess pulled from nowhere. It came straight out of the same physics that gives us both sides of the Hubble tension, the slow, patient math of gravity gathering matter together bit by bit across enormous stretches of time. Then Webb pointed its mirror at exactly that error, and the picture it sent back didn't match the prediction at all. Instead of dim, half-formed smudges, Webb found galaxies that were massive, bright, fully assembled, with clean structure already in place. Some of them appeared to hold nearly as many stars as the Milky Way carries today, a galaxy that took over 13 billion years to reach its current size, matched almost star for star by something that had barely had a few 100 million years to exist at all. Picture planting a seed in the ground and walking away for 2 days. Come back 48 hours later, expecting maybe a sprout, a thin green stem pushing up through the dirt if you're lucky. Instead, you find a fully grown oak tree standing 3 stories tall, its bark thick, its branches spread wide, root system already anchored deep into the earth. Nothing about ordinary growth explains what you're looking at. That's the scale of the gap between what the models predicted for the early universe and what Webb's cameras actually recorded. Researchers didn't just shrug and accept it. They went looking for ways the observation might be misleading rather than the theory being wrong. One idea points to the stars themselves. If the earliest generation of stars burned unusually bright, brighter than stars formed today, they could fool Webb's instruments into reading more mass and more structure than is actually sitting out there. Another idea points at distance measurement itself, the possibility that some calibration error in how cosmic distances get calculated is making these galaxies look closer and therefore younger than they really are. A third idea skips both of those and goes straight at star formation, suggesting these galaxies didn't grow gradually at all, but assembled through extremely compressed, violent bursts of star birth, packed into a much shorter window than usual. Each idea gets tested. None of them close the gap on its own. Bright early stars help a little, but don't explain the full scale of what's showing up. Distance errors, checked and rechecked, don't seem large enough to hide a discrepancy this size. Compressed star formation gets you partway there, but pushed to the extreme, it requires still leaves galaxies more massive than the timeline should allow. This is exactly where early dark energy walks back into the story. Everywhere else it's been treated as a fix for one specific number, a way to shrink the sound horizon and nudge the predicted expansion rate closer to 73. Here, it does something else entirely. A universe that expanded faster during its earliest sliver of existence would also allow structure to clump together sooner, giving matter a head start on forming galaxies before the standard timeline says it should even be possible. It's one of the only proposed fixes anywhere in this entire investigation that reaches into two completely separate crises and offers a single mechanism for both. Physics has spent a century sorting every interaction in nature into 4 boxes, and no 5th box has ever been needed. Gravity holds planets in orbit and pulls galaxies toward each other. Electromagnetism governs light, chemistry, and the current running through every wire in your house. The strong force glues the nucleus of every atom together. The weak force handles radioactive decay, the quiet process that lets certain elements transform into others. Every experiment ever run in a laboratory, from the smallest particle collider to the most sensitive tabletop setup, fits inside those 4 categories without exception. Nobody has ever needed a 5th explanation to make the numbers work. The Hubble tension has revived a question that mostly sat dormant for decades. What if there's a 5th force, one so faint it has slipped past every detector we've ever built, but strong enough over enormous distances to leave a mark on how fast the universe stretches apart? Not something that would show up in a physics lab on Earth. Something that only becomes visible once you're measuring effects spread across billions of light years, the kind of scale no experiment on this planet has ever been able to simulate. Here's the concept that makes a force like that possible without contradicting anything we've already confirmed in the lab. Physicists call it a chameleon field, and the name fits the behavior almost exactly. A chameleon changes its appearance based on what surrounds it. This hypothetical force would change its strength the same way, based on the density of whatever's nearby. Near a planet, near a star, anywhere, matter is packed together tightly. The force would essentially switch off, hiding itself so completely that no instrument built here could ever catch it acting. But out in the vast emptiness between galaxies, where density drops close to nothing, that same force could switch back on, pushing with real strength across distances no laboratory will ever span. That's the entire explanation for why we've never felt it directly. We happen to live in exactly the kind of dense environment where a chameleon field would go quiet. This isn't the first time cosmology has had to lean on something invisible to make its equations behave. Dark matter still hasn't been caught either. For 40 years, physicists have built increasingly sensitive detectors buried deep underground in old mines and disused tunnels, shielded from cosmic rays, waiting for a single dark matter particle to brush against a sensor and leave a trace. Every one of those experiments has come back silent. We know dark matter's gravitational fingerprints are real, spinning galaxies too fast, bending light too sharply, but the particle itself has never shown up. That silence leaves the door open. If something we're confident exists can hide from every detector for 4 decades, a fifth force weak enough to escape the same instruments isn't asking for much more. None of this should be overstated. No fifth force has been confirmed. Nobody has published a discovery, and there's no experiment sitting in a drawer somewhere with a result waiting to be announced. What's changed is the intensity of the search, and it's changed specifically because of the tension between 67 and 73. A gap that size, refusing to close no matter how carefully it's measured, is exactly the kind of pressure that gets physicists looking in directions they'd otherwise leave alone. If a fifth force is ever found, it wouldn't just patch one broken number. It would open an entire sector of physics nobody has had access to before. General relativity has stood for over a century without a single confirmed crack in it. Starlight bending around the sun during a 1919 eclipse. The precise wobble in Mercury's orbit that Newton's equations couldn't explain but Einstein's could. Gravitational waves, ripples in space-time itself, finally caught by detectors full century after Einstein predicted they should exist. Every test physicists have thrown at this theory, it has passed. That track record is exactly why nobody touches it lightly. You don't casually rewrite the most successful theory in the history of science because 2 numbers refuse to agree. But the pressure has built to the point where a growing number of physicists are asking a question that would have sounded reckless 20 years ago. What if gravity itself needs correcting, not with a new particle or a new form of energy, but with a change to the law itself? The core idea behind modified gravity isn't to add another invisible ingredient to the universe's recipe. It's to say the recipe's basic rule for how mass and distance interact might be slightly wrong, in a way so small it stays hidden at the scale of planets and solar systems, but grows large enough to matter once you stretch it across galaxies and beyond. The oldest and most familiar attempt at this goes by the name MUND, short for Modified Newtonian Dynamics. It wasn't built to solve the Hubble tension. It was built decades ago to explain something stranger: why stars at the outer edges of spiral galaxies orbit far faster than the visible matter those galaxies should allow, without reaching for dark matter as the answer. MUND proposes that gravity itself behaves differently once accelerations drop low enough, exactly the regime found at a galaxy's outskirts. It's had real success there. Push it out to galaxy clusters, larger structures with even weaker average pull, and the success gets patchier. It doesn't collapse entirely, but it stops being the clean fix it was at galactic scale. 2 other families sit alongside MO and D, each attacking the problem from a different angle. Frey, gravity takes Einstein's original equations and swaps out a single term, one that describes the curvature of space, for something far more flexible, a function that can bend and adjust its behavior depending on the scale you're looking at. Scalar tensor theories take a different route entirely, adding a brand new field on top of standard gravity, one whose strength can shift and evolve as the universe ages, rather than staying fixed. Different math, different assumptions, but the same underlying ambition. Make gravity itself carry the weight that dark energy has been carrying alone. Every one of these theories faces the same brutal requirement. Whatever correction gets proposed has to vanish almost completely at the scale of our solar system, because Einstein's equations already match what we observe there to extraordinary precision. It has to leave the cosmic microwave background nearly untouched, since that ancient light matches standard predictions with startling accuracy. And somehow, after clearing both of those hurdles, it still has to produce exactly the shift needed to explain today's expansion rate without throwing off how galaxies cluster together or how light bends around massive objects on its way to us. That's an extraordinarily narrow needle to thread. Loosen one constraint to fix the expansion problem, and you risk breaking something else that's already been measured with precision. No version of modified gravity has threaded that needle cleanly, yet none has emerged as the obvious replacement. The theory that quietly resolves the tension while leaving everything else intact. But the fact that serious physicists are running these models seriously, testing them against real data instead of dismissing them outright, says something on its own. Nobody proposes rewriting Einstein for fun. Every fix examined so far assumes dark energy is a real, if mysterious, ingredient in the cosmos. There's a deeper problem sitting underneath all of them, one that shows up the moment you try to calculate dark energy from first principles instead of just measuring its effects. Quantum field theory says empty space is never actually empty, even in a vacuum with no particles, no light, nothing sitting inside it at all. The vacuum itself carries energy, a background hum built into the fabric of physics. That's not a fringe idea. It's standard, tested, accepted physics, confirmed in laboratory experiments again and again. The trouble starts when you try to calculate how much energy that vacuum should actually contain. Run the math using quantum field theory, and the answer comes back roughly 10 to the power of 120 times larger than what astronomers actually measure when they look at dark energy's real effect on the universe. Sit with the size of that gap for a second, because a number like that doesn't really mean anything until you put it next to something you can picture. Imagine predicting someone's height and getting the number wrong by that same margin. Not off by a foot, not off by a mile. Predict 1 inch and then discover the actual person is tall enough to stretch from Earth to the edge of the observable universe and back, and then do that same round trip again, trillions upon trillions of times over, before you've even accounted for the full size of the error. That's not a rounding mistake anywhere close to normal science. That's the single worst quantitative prediction ever produced by a serious physical theory. And it comes from math that works flawlessly everywhere else it's been tested. Here's why this isn't just an embarrassing footnote physicists can shrug off. If that raw prediction were actually true, empty space really carried that much energy, the universe wouldn't look anything like the one we're living in. Space would tear itself apart under that pressure almost instantly, stretching so violently that matter would never have the chance to settle into anything. No atoms would ever form. No stars, no galaxies would ever gather themselves into the shapes filling every telescope image humanity has ever taken. There would be no observers around afterward to even notice the problem, because the raw force implied by that number leaves no room for anything solid to exist at all. Obviously, we exist. Atoms formed, stars ignited, which means something in nature is cancelling out nearly the entire predicted vacuum energy, leaving behind only a sliver, a tiny residual just barely large enough to account for the gentle acceleration astronomers actually observe. And here's the honest, uncomfortable part nobody in physics has resolved. No mechanism currently known can explain how or why that cancellation happens with anything close to that precision. Not a rough guess. An almost perfect erasure of 120 orders of magnitude, leaving behind exactly enough energy to build the dark energy we actually measure, and not one detectable trace more. Now fold everything covered earlier back into this. If dark energy really is holding steady, unchanging one fixed number forever, that cancellation problem is already the deepest unsolved puzzle in physics. But the DS data suggests dark energy might not be fixed at all. It might be weakening, shifting character across cosmic history, the way earlier sections in this investigation laid out. If that holds up, the cancellation mechanism physicists eventually need to find isn't just impossibly precise anymore. It has to be dynamic too, adjusting its own precision as the universe ages. Nothing in known physics does that. Nothing built so far even hints at how it could. Look at what the universe is made of today, and you run into a fact that sounds like nothing more than trivia until you actually sit with it. Dark energy makes up roughly 70% of everything. Dark matter accounts for around 25%. Ordinary matter, the stuff of stars and planets and every person who has ever lived, is stuck at a mere 5%. On its own, that split doesn't look strange. What makes it strange is that these three things don't play by the same rules as the universe expands. Ordinary matter thins out as space stretches. The same handful of particles spread across more and more volume. Dark matter dilutes the same way, dropping in density as the cosmos grows. Dark energy doesn't behave like that at all. In the standard picture, its density stays essentially fixed no matter how much space gets added. 3 ingredients, 3 completely different rates of change, and yet right now, in this particular era, they happen to sit within the same rough order of magnitude of each other. Wind a few billion years and matter would have overwhelmingly dominated, run the clock forward, and dark energy will completely swamp everything else. We exist in the narrow window where the 3 are still roughly comparable. Picture walking into a room holding 3 hourglasses, each one built with a different amount of sand and a different rate of flow. One drains fast, one slow, one somewhere in between. By any reasonable expectation, if you walked in at a random moment, you'd expect to find one nearly full and another nearly empty. Instead, all 3 show close to the same amount of sand at the exact instant you happen to walk through the door. That's the coincidence sitting at the center of modern cosmology, except the room is the entire universe, and the moment you walked in is now. The explanation offered most often is called the anthropic principle, and it's honest about what it is and isn't claiming. It doesn't say the universe was built with observers in mind. It says only observers who exist during a stable enough era would ever be in a position to ask the question at all. Too early, and matter's grip on gravity prevents galaxies from ever settling into anything organized. Too late, and dark energy has spread everything so thin that stars can no longer form, and structure has nothing left to hold on to. Only this narrow stretch of cosmic time allows galaxies, stars, and something complex enough to wonder about hourglasses. So of course, that's when we find ourselves looking. Plenty of physicists accept that reasoning without much comfort. It answers why we're the ones asking the question, but it never touches why the universe happens to be built this way in the first place. It filters which era gets observed without explaining why that era's numbers landed where they did. It's less an answer than a description of who gets to notice the problem. This is exactly where the DESI findings change the shape of the argument. If dark energy behaves as a fixed constant, forever unchanging, then this balance really is a staggering fluke. Three unrelated quantities landing near each other by pure chance. But if dark energy rises and falls, the way the newest data suggests, weaker in some eras, stronger in others, then moments of rough balance between the three ingredients stop being a 1,000,000,000,000 accident. They become something closer to a predictable phase, a stretch of cosmic history that any evolving universe would eventually pass through on its own. Every method covered so far, from Cepheids to red giants to the cosmic microwave background, depends on some kind of calibration chain, a ladder of assumptions climbing from nearby stars out to the edge of the observable universe. There's one method that skips the ladder completely, and it doesn't rely on stars at all. It relies on the shape of gravity itself, massive galaxies sitting between us and something much farther away bend the light passing near them. Einstein predicted this a century ago, and by now it's been confirmed so many times it barely counts as news. But every so often, the alignment is precise enough that the bending does something stranger than a simple deflection. A distant quasar, one of those blazing cores of feeding black holes, sits almost directly behind a foreground galaxy. And the galaxy's gravity splits the quasar's light into multiple separate images scattered around the foreground galaxy like reflections in a cracked mirror. Same quasar, same light, arriving at Earth from several different directions at once because gravity bent each path differently on the way here. Here's what makes this useful for measuring the universe, rather than just a strange picture for astronomers to admire. Each of those bent paths is a different length. Light, following one route around the lensing galaxy, travels slightly farther than light following another, which means the images don't arrive at exactly the same moment, even though they started from the exact same source at the exact same time. Quasars aren't perfectly steady. They flicker, brightening and dimming in small, irregular fluctuations as material swirls into the black hole powering them. Catch that same flicker showing up in one image, then watch for it to show up again in a second image days or weeks later. And you've measured a real-time delay, a gap you can convert directly into distance using nothing but the geometry of the bending and the physics of how light travels. Notice what's missing from that entire process. No Cepheid pulse cycle. No white dwarf detonating at a fixed brightness. No calibration chain stretching backward through supernovae to stars close enough for parallax. This method never touches a single one of those rungs. It measures distance from the shape of space-time around a massive galaxy and the timing of a flicker crossing multiple paths, full stop. If Cepheids or supernovae were hiding some subtle stellar bias baked into their physics, a bias nobody's caught despite years of scrutiny, this method wouldn't inherit it, because it never uses those stars in the first place. Collaborations running this exact technique on real lensed quasars have landed in the mid to high 70s, sitting comfortably alongside the local side of the tension, rather than drifting toward Planck's number. That result came from a completely different set of physics than anything discussed earlier in this investigation. No distance ladder, no calibration chain, nothing borrowed from the star-based methods that critics have spent years picking apart. That's the real weight of this result. It isn't just one more measurement landing in the 70s. It's a measurement that had no way of inheriting a Cepheid problem or a supernova problem, arriving at the same high number anyway. Every argument that the local side of this tension rests on some undiscovered stellar bias just got harder to make, because gravitational lensing never went anywhere near a star to get there. August of 2017. Twin detectors, one buried in the Louisiana countryside, the other tucked into the high desert of Washington state, catch something neither had ever recorded before. A ripple passing through space-time itself, arriving at both instruments within a fraction of a second of each other. The source: two neutron stars, the collapsed cores of dead stars, packed so dense that a teaspoon of their material would outweigh a mountain, spiraling into each other and colliding 130 million light-years away. Gravitational wave detectors had caught mergers before this, black holes crashing together, sending the same kind of ripple across the cosmos. But black hole collisions happen in total darkness. Two black holes merge, and nothing escapes to tell any telescope where to look. This event was different. Neutron stars carry actual matter, and when they collide, that matter doesn't just vanish into the merger. It gets flung outward, heated, ignited. Light poured out of this collision in multiple wavelengths, and within hours, telescopes around the world had turned toward the same patch of sky the gravitational wave detectors had flagged, catching the afterglow directly. For the first time, scientists had both a ripple in spacetime and a visible light source tied to the exact same cosmic event. That combination unlocked something the field had wanted for decades. Gravitational waves carry within their shape a direct readout of how much power the collision released. No calibration star required at any step. A distant galaxy dims a supernova's apparent brightness by an amount that depends on distance, and you calculate that distance by comparing what you observe to what you'd expect at a known brightness. Gravitational waves skip that comparison entirely. The waveform itself, the pattern of stretching and squeezing traced out as the ripple passes through a detector, encodes the true power of the merger directly from the physics of how two massive objects spiral together. No white dwarf detonation. Just the raw signature of gravity and motion, readable straight off the instrument. Astronomers call this method the standard siren, a deliberate echo of the standard candle language used for supernovae, except here the light itself isn't the ruler. The wave is. Combine the wave's inferred power with how faint it arrived at the detectors, and you get a distance. Combine that distance with the redshift measured from the light left over from the collision, and you get an expansion rate calculated from a method that never touches the distance ladder at any rung. The 2017 event alone produced a value hovering around 70 kilometers per second, Enican per minute, megaparsec, sitting almost exactly in the gap between the two camps. This investigation has spent so long mapping. The uncertainty attached to that number was large, wide enough that nobody treated it as a verdict on anything. One detection doesn't settle a debate this deep, but it didn't need to settle anything to matter. What it offered was a completely independent line of evidence, built from a method with no shared assumptions, no shared calibration, no shared vulnerability to whatever might be quietly wrong with stars or ancient light. Since that first event, more neutron star mergers have been caught, each one adding another independent data point to the same growing picture. The uncertainty on this method keeps narrowing as the catalog grows, and every fresh detection sharpens the range a little further. What hasn't happened, not once, across any of these mergers, is a result drifting down toward Planck's number. The standard sirens keep landing somewhere in the same general territory the local measurements have occupied all along, a pattern that holds regardless of which physics you use to get there. Step back from any single method for a moment and look at the whole battlefield at once. Line up every result this investigation has walked through so far, and a pattern emerges that no individual measurement could show on its own. Start with the local side, the present-day universe, measured directly. Cepheids feeding into supernovae give SH0ES a number sitting right around 73. Red giant stars, calibrated through an entirely different physical process, land somewhat lower in the neighborhood of 70. Gravitational lensing, built from nothing but the bending of light around massive galaxies, comes in at the low to mid-70s. Gravitational waves, the standard sirens pulled from colliding neutron stars, hover in that same general 70s range, wide uncertainty and all. 4 separate methods, 4 separate sets of physics, 4 separate teams of researchers who don't share a calibration chain, a telescope, or in some cases even a home institution. And every one of them lands in the same rough territory. Now, put the early universe side next to it. Planck's reading of the cosmic microwave background gives 67.4. The Atacama Cosmology Telescope, a completely different instrument staring at the same ancient light from a mountaintop in Chile, comes back near 67. The South Pole Telescope, built with its own separate design and its own separate team, lands in that same neighborhood. Baryon acoustic oscillations, that frozen ripple pattern locked into the early universe, point the same direction again. 4 more independent efforts, and every one of them clusters tightly around the low 60s into the high 60 range, refusing to drift upward no matter who's running the numbers. Here's the part worth sitting with. This isn't one strange result standing alone against a wall of agreement. If it were, you'd suspect a mistake in that one outlier and move on. What's actually on the table is 2 separate clusters, each one internally consistent, each one built from multiple independent teams using multiple independent techniques. And neither cluster comes anywhere close to touching the other. That structure rules out the easiest explanation before it even gets off the ground. If this whole tension were nothing more than noise, some accumulation of small random errors scattered across dozens of experiments, you wouldn't get 2 tight clusters sitting on opposite sides of a gap. You'd get scatter. Revolts smeared across a wide range, some high, some low, some landing right in the middle. The way sloppy measurements always behave when nobody's found the real answer yet. Randomness doesn't organize itself into 2 disciplined camps and then stay there for over a decade while telescopes keep improving. Noise fades as instruments get better. This gap hasn't. So look at what actually separates these 2 camps, because it isn't randomness and it isn't which building the telescope sits in. It's when the light being measured was emitted. Every method landing near 67 is reading something ancient. Light and structure locked in place, hundreds of thousands of years after the Big Bang. Every method landing near 73 is reading something close to now, stars and galaxies as they exist in the present moment of cosmic history. Early universe, low. Consistently, repeatedly, regardless of which physics gets used to take the measurement. That divide falling cleanly along cosmic time rather than along instrument type or research team points the finger somewhere specific. The flaw almost certainly isn't hiding inside any single measurement, because too many unrelated measurements keep confirming both sides independently. It's hiding somewhere in the bridge connecting them, in whatever physical process is supposed to carry the universe smoothly from its ancient expansion rate to its present one. Something happens between then and now the current models aren't accounting for. And every fresh result just keeps confirming that the gap sits exactly there. Not every scientist trying to pin down the Hubble constant starts from Cepheids. One of the loudest alternative voices in this entire debate belongs to Wendy Friedman, and her name carries weight for a reason. Back in the 1990 seconds, she led the team that first nailed the Hubble constant down to within about 10%, using the original Hubble Space Telescope in one of its earliest and most important missions. That work helped settle a debate that had raged for decades over whether the universe was 10 billion years old or 20. Friedman isn't some outsider challenging the field from the margins. She helped build the field's foundation. And now she's leading a team arguing that Cepheids might not be the reliable rung everyone assumes them to be. Her alternative doesn't touch pulsing stars at all. It uses something called the tip of the red giant branch, and the physics behind it is almost stubbornly simple. As a star burns through its life, it eventually exhausts the hydrogen fueling its core, starts to swell, cooling and reddening as it grows into what's called a red giant. That expansion continues until the star hits a very specific, very predictable peak in brightness, right before its core gets hot enough to ignite a new fuel source, and the star's behavior shifts entirely. That peak brightness, the tip of the red giant branch, turns out to be remarkably consistent across different galaxies. Measure how bright it appears from Earth. Compare that to its known true brightness, and you've got a standard candle that never touches a Cepheid pulse cycle at any point in the calculation. Friedman's team ran this method using their own careful measurements, and the number they landed on sits in a strange spot, somewhere between 69 and 70, lower than the 73 that SH0ES has defended through years of scrutiny, but still sitting noticeably above Planck's 67.4. Not quite either camp. Comfortably parked in the space between two positions that were supposed to be the only two options on the table. That result set off exactly the kind of dispute you'd expect between two teams who've each spent decades refining their own methods. And SH0ES argues that identifying the precise tip of the red giant branch carries its own hidden uncertainty, that pinning down the exact moment a star's brightness peaks before it shifts fuel sources is harder than Friedman's team gives it credit for, and that subtle errors there could be dragging her number down artificially. Friedman's team fires back with the opposite accusation, that Cepheids carry their own quiet biases, contamination from dust, from crowding, from subtle differences between one galaxy's stellar population and another's, biases that have simply gone unnoticed because nobody's had a strong enough independent method to catch them until now. Here's what actually matters buried inside that back and forth. Nobody in this dispute, on either side, gets anywhere close to 67. Even if you accept every criticism Friedman's team levels at Cepheids and abandon that method completely, trusting red giants instead as the cleaner, more reliable candle, the answer still doesn't fall down to match Planck. It lands at 69 or 70, still meaningfully separated from the early universe number by a gap too wide to explain away as noise. Throw out the entire star system SH0ES built their case on, and the tension doesn't vanish. It just moves a little closer to the middle and refuses to close the rest of the way. Every measurement covered so far assumes the evidence sitting in front of us will still be there tomorrow. It won't. Cosmic expansion isn't a static backdrop against which astronomers take readings. It's a process actively carrying galaxies away from us, and past a certain point, that process doesn't just make a galaxy fainter or farther. It removes that galaxy from view permanently, dragging it beyond a boundary its light can never cross again. Here's the argument associated most directly with physicist Lawrence Krauss, and it's the kind of idea that changes how you look at every telescope image you've ever seen. Push the clock forward far enough, tens of billions of years, and any observer sitting in the Milky Way would look out at the sky and find nothing. No distant galaxies scattered across the dark. No cosmic microwave background humming faintly in every direction. The ancient light this entire investigation has leaned on again and again to calculate what the early universe was doing. All of it gone, carried past the horizon by the same expansion Hubble first caught sight of in 1929. An astronomer living in that era, working with instruments as good as anything we have today, would look at a sky that appeared static, isolated, eternal. They'd have every reason to conclude the universe never expanded at all. They'd be completely wrong, and there would be no way for them to find that out. Sit with that for a second, because the temptation is to file this away as a problem for the distant future, something that matters to nobody currently alive. That's not quite right. This erosion isn't a switch that flips on at some far-off date. It's already running. Some of the most distant galaxies visible in today's deepest surveys are already slipping past the cosmic horizon as you read this. Their light stretched thinner and thinner, drifting toward frequencies no instrument will ever recover. The total pool of evidence available to study the universe isn't fixed. It's shrinking, quietly, every single year. That raises a question this entire investigation has circled without naming directly. What if some of the answers to the Hubble tension, to the fading dark energy DSI keeps hinting at, to whatever mechanism actually bridges the early universe and the late one, were once visible, not hidden, not too subtle to catch, simply present in the sky at some earlier point in cosmic history, sitting in light that reached Earth before any telescope existed to record it, and then gone, swallowed past the horizon before Planck, before SH0ES, before anyone thought to build an instrument capable of reading it. That's not a comfortable thought, it shouldn't be. But it also reframes everything the next generation of telescopes is racing to do. Every survey mapping the cosmic web, every instrument cataloging galaxies by the tens of millions, every mission built to squeeze one more decimal point of precision out of an expansion rate is in a real sense working against a clock that never stops. Not a race against a rival research team, a race against the universe itself, quietly filing away its own evidence, one galaxy at a time, past a horizon that never gives anything back. Every question raised across this investigation eventually runs into the same wall. Not enough data. Not yet enough precision to force a verdict. That wall is coming down over the next several years, and it's coming down because a handful of instruments were built specifically to demolish it. DESI hasn't stopped collecting galaxies. The catalogue that already produced those unsettling hints about weakening dark energy is still growing, still adding new redshift night after night from that mountain in Arizona, climbing toward a target of roughly 40 million objects by the time its survey wraps up. That matters because a hint sitting at a few sigma of confidence can go one of two ways. As the sample size grows, it can sharpen into something undeniable, the kind of result nobody can wave away as statistical noise. Or it can soften, drift back toward the boring constant everyone assumed for decades, revealed as a fluctuation that looked meaningful only because the early data was thin. DESI's next few years will settle which of those two futures is real. Euclid is running a parallel operation from an entirely different angle. Launched in 2023, this European space telescope has one job: map the shapes and positions of over 1 billion galaxies across a huge stretch of sky. Not their brightness, their shapes. Because light bends slightly as it passes near massive structures on its way to us, and the accumulated distortion in a billion galaxy shapes carries a readable signature of how matter clusters throughout cosmic history. Euclid is built to test three competing pictures at once. Dark energy a fixed constant, exactly as the textbooks assumed for decades. Is it evolving the way DAASC's data seems to suggest? Or does the real answer lie somewhere in modified gravity, a correction to Einstein's equations rather than a new ingredient in the cosmic recipe? Euclid's data will bear on all three. Then there's the Vera-Rubin Observatory, a ground-based instrument built for a different kind of coverage entirely. Instead of staring at one patch of sky for a long exposure, Rubin will sweep across the entire southern sky every few nights, over and over, building what amounts to a time-lapse movie of the universe. Buried in that constant resurvey is an expectation of millions of new supernovae, caught early, tracked as they brighten and fade, feeding directly into the same distance calculations SH0ES has spent years refining. Rubin isn't just adding one more data point, it's adding volume, the kind of statistical weight that turns a suggestive pattern into an undeniable one. Two more instruments round out this coming wave. The Roman Space Telescope will run wide-field infrared surveys, reaching galaxies too faint or too red for older instruments to resolve clearly, adding its own independent measurement of expansion at multiple points in cosmic history. The Square Kilometre Array takes a completely different approach, mapping hydrogen gas through radio wavelengths across enormous stretches of time, tracing the structure of the universe, using signals no optical telescope can see at all. Neither project shares a calibration chain with SH0ES, with Planck, or with each other. Each one is another independent test of the exact same numbers this entire investigation has been chasing. Put these together, and the honest expectation among researchers is a resolution within roughly 5 to 10 years. Not a guess about timing pulled from optimism. A direct consequence of how much new data is about to arrive and how many independent methods will finally be pointed at the same unresolved question simultaneously. One of two things happens once that data lands. Either the case for new physics becomes impossible to avoid, confirmed from enough angles that no single systematic error could explain it away, or somewhere in that flood of data sits the one overlooked flaw that's been hiding in plain sight the entire time. The calibration error nobody caught because nobody had the resolution to catch it. Either outcome ends the wait. Neither outcome is guaranteed yet. Every scenario walked through so far assumes an ending. New data arrives, one side buckles, the gap closes, and cosmology moves forward with a single trusted number again. Ask the harder question directly. What happens if that never comes? What if DSI finishes its full catalogue, Euclid completes its billion galaxy survey, Rubin finishes its decade of nightly sweeps, Roman and the Square Kilometre Array deliver everything they were built to deliver, and 67 and 73 are still sitting there, unmoved, exactly where they've been for over a decade now? That outcome isn't unprecedented in physics. Dark matter has been a confirmed gravitational signature without a confirmed particle for close to 90 years, stretching back to observations of galaxy clusters in the 1930 seconds. Generations of physicists have built careers, run experiments, and retired without ever seeing that mystery close. 90 years is a long time to leave a question open. If the Hubble tension followed a similar arc, it wouldn't be leaving the field of physics. It would be joining a small, uncomfortable list of problems that refuse to resolve on any timeline anyone finds convenient. Picture what that actually looks like inside the field, day to day, decade to decade. Textbooks would need to stop printing a single confident number for the expansion rate of the universe and start printing two, side by side, with a caveat explaining that nobody has reconciled them yet. Researchers would sort themselves into camps, not by personality or ambition, but by which measurement they've come to trust more. Early universe loyalists building careers around the cosmic microwave background. Local universe loyalists building careers around Cepheids and supernovae and lensing. Grant funding would keep splitting down that same fault line. Agencies backing both sides at once because nobody can say with confidence which one is about to be proven right. Entire conferences would organize themselves around the divide instead of around a shared consensus. That would not be a failure. It's worth stating plainly because the instinct is to treat an unresolved mystery as a shortcoming. Evidence that scientists somehow didn't do their job well enough. That instinct is backwards here. Attention surviving every test thrown at it for over a decade, confirmed independently by methods with nothing in common, isn't a sign of sloppy measurement. It's a sign that the universe is handing physics something genuinely structural, a real crack in the framework, rather than an arithmetic slip somebody eventually catches. Science doesn't fail by encountering a problem too deep to solve quickly. It fails by pretending the problem isn't there. There's a quieter possibility worth holding on to as well, one that doesn't require a revolution at all. Physics has a history of tensions that looked unsolvable for years and then simply dissolved. Not because some new law of nature got discovered, but because somebody found the one overlooked calibration error sitting quietly at the base of a chain of assumptions nobody had thought to question. It happens more often than the dramatic version of this story likes to admit. The Hubble tension could still end that way. Not with a new force, not with a rewritten equation for gravity, just a correction buried somewhere. Nobody's looked closely enough yet, waiting to make both numbers agree. The moment somebody finally spots it. Go back to the beginning of this investigation. Two scientists, opposite ends of a hallway, both holding rulers, both measuring the same wall, both refusing to be wrong. That image was never just a way to open a story. It's the entire crisis compressed into a single picture, and every chapter since has just been walking down that hallway a little further, checking the rulers, checking the wall, finding nothing broken in either one. So gather up what's actually on the table now, without repeating the case built for any of it. Dark energy might not be the fixed, eternal constant Einstein first scribbled down and later called his blunder. It might rise and fall, weaken and strengthen, behave in ways nothing in the standard model currently allows. Time itself might not move at the same rate everywhere, might run faster in the empty stretches between galaxies and slower inside the crowded structures where matter piles up, an unevenness large enough to fake an acceleration that was never really there. Gravity, the most tested theory in the history of physics, might still need a correction at the scale of the whole cosmos, invisible anywhere smaller. Or the missing piece might be something nobody's caught yet. A particle, a force, a field, sitting just below the threshold of every detector built so far. None of these stand on equal footing. Some carry more supporting evidence than others. Some have already survived tests that would have killed a weaker idea. But here's what matters more than ranking them against each other. Every one of them is being taken seriously right now, argued over in real journals, tested against real data, by physicists with real reputations on the line. Not one of these ideas lives on the fringe anymore. They live in the mainstream of a field that has run out of easy explanations. Look closely at what actually connects them, because it isn't the physics, It's the admission sitting underneath all of it. Every single one of these possibilities requires accepting that some assumption physicists have leaned on for decades. Something taught in classrooms as settled fact might simply be incomplete. Not wrong in some careless, sloppy way. Incomplete, the way a map can be accurate for the territory it was drawn to cover and still miss everything lying past its edge. Physics has stood at this exact edge before. Newton's gravity explained the motion of planets with such precision that for 2 centuries nobody thought there was anything left to find, right up until Mercury's orbit refused to behave the way the equations demanded, a small discrepancy nobody could explain away. Classical mechanics described the physical world so completely that physicists, the end of the 1800 seconds, spoke openly about physics being nearly finished, with only a few decimal points left to sharpen, right before the quantum world cracked that confidence apart entirely. Both times, the old framework wasn't torn down out of malice or fashion. It simply stopped matching what careful, repeated measurement kept insisting was true. And both times, what replaced it was stranger than anything the old framework could have imagined, and somehow, underneath that strangeness, more true. Right now, tonight, while you sit with all of this, not waiting for a conference to settle the matter, not pausing while 2 teams of careful, honest scientists finish arguing. Space is stretching at 67 kilometers per second, econd per minute gigaparsec, or 73, or some quiet third number nobody has landed on yet, and it is doing that whether or not a single human being agrees on which figure belongs in the textbook. The disagreement lives entirely on our side of the telescope. The universe has no side in it at all. Look up tonight, if you get the chance. Some of the light hitting your eyes left its source before Adam Rees ever pointed a telescope at a Cepheid, before Planck ever mapped a single degree of the cosmic microwave background, before anyone had drawn a hallway with 2 rulers in it. That light has been crossing empty space for longer than the argument over its meaning has existed. It carries no number stamped on it, no preference for 67 or 73. It simply arrives the way it always has, indifferent to which camp eventually turns out to be right. What ends? This isn't going to be a clever new equation scribbled onto a chalkboard in a single afternoon. It's going to be patience, the unglamorous kind, the kind that looks like a satellite finishing its 5th year of data collection, or a ground-based survey completing its 10,000th night of scanning the same stretch of southern sky. Euclid still has years left in its billion galaxy survey. Rubin has barely started his nightly sweep. Desi's catalogue is still growing toward numbers nobody's fully processed. None of the telescopes capable of forcing a real verdict have finished their work yet. The answer isn't hiding behind some insight waiting to be had. It's hiding behind data that hasn't been collected. So here's where this investigation actually leaves you. Not with a number to write down and trust. Not with a villain unmasked or a mystery solved. With 2 honest measurements, each defended by careful people who check their work more times than most of us check anything in our lives, refusing to meet in the middle. Somewhere between that 67 and that 73 sits a fact about reality nobody alive has fully seen. Not yet measured cleanly, not yet named correctly, not even fully imagined by anyone working on this problem today. It is out there right now, encoded in the light still falling toward Earth, in the galaxy still slipping past a horizon we can't get back, in whatever bridge actually connects the ancient universe to the one we're standing in. Waiting patiently, the way it always has, for someone to finally measure it right.